So there are a couple things you're starting to realize as you've done these. For example, just in this worksheet, you've already made kind of an inference about what the integral from like a to a is. You've made an inference about what it means to go from like to do the integral from b to a, where a is less than b. And you've also made like taking a and b. I think taking a, b, and c together from your warm-up today makes me think that like maybe there's this like kind of additive property. We're going to try and be real clear about those today. And again, try to really feel like we understand what that integral sign means a little more, what we can even do with it, what algebraic properties it might have. The first thing we should say is like when it doesn't even make sense to ask the question, like what f of x can we stick inside there? Remember we had that question when we were talking about differentiation. We were like, is it always a question that makes sense to ask what is the derivative of this function at this point? Or we get sometimes that, is this function differentiable? And we added like the a-b-l-e on the end, like is this differentiable? And we said it's not differentiable if there are any points at which the derivative fails to exist. The bar is much lower for integrable functions. All it has to be is continuous. And actually the bar is even lower than that, but I don't really feel like talking about it. Okay. The point is like, can we find the area under almost anything? And the answer is like, yeah, right? Like there's very few things that it doesn't make sense to like calculate the area under. It was a much higher bar for differentiability, wasn't it? Actually has to be like smooth and stuff. I don't have anything else to say about that. Okay, I just wanted to say. Now let's actually launch into some of the properties, many of which you've already discovered as you've been thinking about this. This one can be explained by what Judah said. Judah, can you just say it again, and this time I want you to like listen carefully.
If you're multiplying f of x and dx and they're both negative, then it's positive. Then f of x and dx is positive.
Yeah, and this doesn't necessarily, if f is positive, then that argument still holds. But the point is, if you're like integrating backwards, you heard Rosa and Judah's explanation of that. Yeah, I mean, think about Riemann sums. Like, imagine if you were actually calculating those rectangles, then you have dx's that are negative, don't you? The change in x will be taken to be negative. As you march from b to a, you get opposite sign. So sometimes that means two things. If you're integrating backwards and your function is above the x-axis, then you get a negative result. But then also the situation that just arose right now in the warm-up, if you're integrating below the x-axis and you're doing it backwards, then you actually get a positive result. So both of those things can happen. Again, it comes from the fact that this is defined in terms of that sum. Remember, it's the limit of a Riemann sum is what this is. So always go back and think about this as being a rectangle. That's all. In fact, every single one of the properties we proved today can be talked about here, can be thought about in terms of the Riemann sum, right? You go back to the rectangle. So, I mean, we can draw pictures on that, but I'll only explain more on number one if you feel that's necessary. Then this was the other property you just discovered a minute ago too, is that this makes sense. Again, you could think like in terms of the rectangles, like the change in x is necessarily 0, so it doesn't matter what f of x happens to be. Hopefully we're not like blowing anyone's mind too much yet, especially with that one. But these aren't things that need to be like said. So here we are, we're saying them. This one I don't feel like came up maybe at all yet, but let's come out and say it. Turns out you can factor out a number from an integral. We could, I don't know, can we prove this using Riemann sums too? Let's see if we can think about that in terms of rectangles. If you have, well, I guess this just follows on from the property of summation. Did you know that you could do that with a sum? If you have a sum, every property of summation that you know applies to integrals, right? Because they're just sums. Okay. So I don't know if you knew that you could do this with a sum. Really, essentially, it's just factoring it out from that set of parentheses, right? Like if you actually add up. In fact, you've already been using that property whenever you do a Riemann sum. A lot of times you factor out a number just because you're lazy. You like, I don't feel like I'll multiply afterward, you know. So this property is really just that property said that way. Again, we could draw pictures too, but I think that says enough, maybe. Sum and difference. That is to say, if you do the following, this works. Again, this is like follows directly from a property of summation that you might know from working with sums in pre-calc. Notice this is the same limit of integration here, a and b, a and b. There was one on the homework last night, someone was asking me as I walked around, that said, how can you write, I have no idea what the problem was, but it was like, you know, you had something like this. I don't remember, I'm making this up, but it was something like that, and it asks, like, how can you write that as one integral? And I don't know how we were expecting you to know that without having thought about this first. So now you can go back and do that problem. It's not this, I think it's different. It's got to do that. It's 2x, okay. Is it 0 to 5 though? No. Something doesn't matter, doesn't matter. The point is, you can write that as right? You can combine those. And again, prove that using, you can, if, again, you could write this in terms of sums, right? If you have the sum of two sequences that are combined, isn't that the same as that, right? All that, again, all that is like a rearrangement of terms, right? If you write this sum out, it's like almost not worth writing out, but if you write this out, all the terms of an, this is just a finite sum, and all the terms of bn, are you allowed to rearrange those so that you have an plus bn, ai plus bi for all the I between 1 and n? Yeah, you can do that. Because addition is like commutative and associative. You can rearrange that sum. So that should make sense, and that's a very helpful property actually. And then additivity you used in parts A, B, and C of your warm-up today without even thinking of, like, of course it has this property because, like, I know area does. Look carefully what's written there and look at the limits of integration. Does it make sense? Interpret that yourself geometrically, why that makes sense, like the picture makes sense there. Like the sum of the parts equals the whole is basically all that's saying. So many of these are not necessarily rocket science, but they are properties that you'll be using, and you need to be aware that you are allowed to use them. Okay? There's one more property I want to share. It's kind of a non-property too, but I'll wait for a second. Oh, actually, I think I have a picture of the additivity there.
Write it down.
All right, good. It just struck me just now that, by the way, if you want, like, I know you can't find yet, you don't know how to find the exact area under, without a calculator, the exact area under the curve when it's like a parabola or something. But it does strike me as interesting that you could actually, right now with these properties and what you already know, you could actually find the area between two parabolas not too bad. Like, say this was like, I don't know, this guy here was, this downward facing parabola was like negative x squared plus 3. And this guy was like x squared minus 4 or something. I don't know. You wanted to find the area between those. No, just kidding. I'm trying to think of another good example here. What if this was what if this top one was x squared just make it x squared. And this bottom one was like x squared what is this, minus, how about like 4 and 1? Let's make those zeros something nice. Something like that. So could you find the area between those? I think the answer is yes, because on some interval, right? If I asked you to find the area between those, I think you could, because just using stuff you already know, geometry, because this area here, underneath this would just be this integral, and this dx, and this would be this integral, x squared minus 3x minus 4 dx. And notice when you do this, apply this property here, right? Kind of like what we did here. The x squareds go away, right? So you just get the integral of 3x plus 4 dx. And that's a line, right? So actually, this property does maybe gain access to some interesting problems for you already. Even though it might be like, well, that's curvy. I don't think I can calculate the area between those. Like, actually, maybe you can. 3x plus 4 is something you can integrate without any high technology. These are non-properties, like I said. So I'm not listing those properties. But similar, this shouldn't surprise you. It's similar to the derivatives. There's no product or quotient rule for integrals, though, necessarily. We don't have a nice property for you. In general, these are very, very hard problems. There's no way to, like, because you know the integral from a to b of f, and because you know the integral from a to b of g, does not gain you access at all to the integral of their product. Sorry. You just have to live with that. These are non-properties. They both. Yeah, don't do those things, please. And actually, in the homework, we have some kind of some troll problems like that. Okay, so don't, like, if we have something like that, be like, give frowny face or something. It'll be like not possible or not enough information or something. So just be aware that that's something you might wish were true, but isn't. Sorry. Again, that stems from the fact that, like, is the sum, can you multiply sums and have them be the same as the product of the two arguments of the sums? No, that's not a property of sums that we have. Yeah. Is that good, or are we good? I'm gonna now throw a couple problems at you. Try and just practice these properties a little bit. So try these with your table, and in a minute we'll come together and see how you guys did on them. Okay. Again, try to apply these properties wherever you think they might be useful.
Dude. Sorry, what? Oh yeah.
Which one do you want? Yeah, which one do you want? All right, let's. Was that enough time? No, you need another minute. 10 seconds. Oh, there's not like a copious amount of calculations that are required here. So, all right, for A, now the thing that might have thrown you off there is like the fact that it doesn't seem like there's a function at all. Like what's going on there? Can I ask that question? But you were able to answer it. What'd you say? 7. Talk to us about the reason. On each one of these, maybe you can give a little explanation too as I call on people for these.
Functions like 1 and dx like 7.
Yeah, no, I hesitate, and Rosa did this earlier, but I didn't correct her either. The dx is not 7, just so we're aware. The dx is like still infinitely small, okay? But you're right that this is asking for the area under just a line, a horizontal line. So the answer is 7, but the only part I reject is you calling dx 7. So dx is not 7, but the whole thing is 7, yeah. Yeah, just think geometrically about these. You know, we're still thinking about geometry here a little bit. Christina, what about B? 2 pi. Someone else agree, please? What's up? Don't say it with a question mark at the end, though. Do whatever you do with confidence. Is it? Why?
Because it's a semicircle. Oh wait, just kidding. It's going from 2 to -2.
Okay. All right. What about C? Judah, what'd you say there? I don't have anything else to say about that. Okay. Nicholas, what about the last one? Oh yeah, that's a little awkward. Yeah, sorry.
My name's not Nicholas, it's just Nick.
I know. I just meant, but it could be sounded as true.
Oh, you're good.
I did call him Nicholas. What do you think for that last one? That's a tricky one, maybe. Huh? 18.8. Yeah, okay. Which is what? Also known as, what is it also known as? 6 pi, yeah. Yeah, so 6 pi, which is just 3 times 2 pi. Why does that work out? What property are you using? Like in each case, we could actually maybe formalize this. Like what property are you using there? Yeah, the constant multiple rule that we gave earlier, that you can factor out that 3, and if you already know the answer to the previous problem, which you definitely had thought about already, then just multiply that answer by 3. Which, by the way, that provides like some insight into maybe how you calculate the area of this graph, which is not a semicircle actually. What is it? Yeah, it's kind of bigger this way. It's like vertical stretch on the graph. It is. It's an ellipse. We'll use the math word ellipse. Yeah. So the top half of an ellipse. Do you know how to find the area of an ellipse? Maybe you never knew that before. How do you find the area of an ellipse? Area of a circle is pi r squared. What do you think the area of an ellipse is? It's very elegant.
Pi major x is minor x?
Yeah, that has to be the semi minor and major axis. So like if A is the semi major, and I don't know which one is which here, but if this A is the semi major and B is the semi minor axis, then it's just pi times AB, right? If they're equal, then it's still just pi r squared then, right? Maybe you can also, maybe it's not right to do this. I don't know, but maybe you could also like guess at what the volume of an ellipsoid is too. Can you imagine? You know what I'm saying? It's just a stretch of a sphere in one or more directions. You know, think about what the volume formula might be for that too. I don't know. Yeah, you don't I like to ask an interesting question. You know, throw that out there. There you go. Okay, let's return. We just calculated the area of an ellipse. That was exciting. That's all. I just had to stop and appreciate that moment. Half of an ellipse, at least. The top half of an ellipse. We should all stop and recognize that that's on the video too. There, that's good. Okay. All right. Okay. When you're ready to like actually think about what this question says, we can come back. It's an interesting question. Keep in mind here that the function f is not y equals 10. Like that's not the function f. Is that clear? We have no idea. It could be some crazy curvy function f. I'm just telling you that the integral of f from 0 to 5 is 10. That's all I'm telling you. So work it out with your group. I don't want to give it away yet. Take a chance to think it through. All right, who's willing to talk through this? Jonathan, you want to talk through how you think about this?
Well, let's think about this in terms of. I mean, we have this sum property, right?
True story.
So that's not how I would put it. The sum property states that the integral from 0 to 5 of f of x plus the integral from 0 to 5 of x is equal to so we already know that the integral, we already know that the left integral is equal to 10. And the right integral is basically a right triangle. If you think about the graph of x, it's just like half the square.
Okay.
Half of the square of length 5 is 25 root 2.
25 root 2.
Yeah.
Say, wait, what did you say?
So half of the square of side length 5 is 25.
25 over 2. Yeah. I thought you said 25 root 2 at first. Yeah, and I don't know if we can say, can we say anything else? We could combine those fractions or not, whatever. I'll just leave it that way. Okay. Or you could just, well, actually, I don't know. Maybe you want to write it as a decimal. That'd be nice. 22.5. I might do that. All right. I should have asked. Is that cool? Is that your reasoning too? We just added these two things. This is 12.5. Where did the 25 over 2 come from? Can someone else explain that again? Jonathan did a nice job explaining, but maybe you want to hear it from Stephen, though. Yeah, we're trying to resolve this.
Yeah, so the function is x, so if we plot x in relation to the x, y axis, and yeah, you just find the
however you want to think. You can think of a half a square, like Jonathan said, whatever. Okay, good. All right, now this is another kind of creative problem here. So when you're ready, see if we can compute this. Again, the one thing I want to highlight here is that the area of the regions is denoted by P and Q. The area of this region is P, just to be clear. The area of this region is Q. Does that make sense? I mean, I warn you about that because we've had a discussion about area yesterday. So when I say the area of that region is P, what that means something to you. So again, let me let you struggle with it for a minute, and then we'll see how you do. To 14. So what's that first thing? That's definitely, that's 3Q. There's not much to say. This one's interesting though. I'm interested to see what happens there. So this is 3Q. All right, now I need to think about what the integral from -1 to 14 is. Help me out with that. Yeah, it's negative P plus Q. Yeah? All right, that was the interesting part of this question. But can someone explain, someone else can come behind here and explain why is that negative? I think I get the plus Q, but why is the integral from here to here, yeah, definitely Q I get, but why is the integral from here to here negative P?
Oh, because minus and negative cancel it out.
Good. Nick, does that make sense to you?
I didn't.
You just answered your own question. That's perfect. Thank you. Normally I would like to try and go back and see if you understood it, but I think you understand it. All right. And then you can resolve that. That's what is that? 2Q plus P. All right. More practice. There are 2 worksheets. You guys get the second one. All right, everyone get both worksheets. Okay, they're both due on Monday. Notice too that they both have a front and a back. I think you'll find that each one takes you an average of like 10 seconds. So I think you'll be all right. I'm serious.
Val's Bank,
Bye, guys.
come to the main office. Val's Bank to the main office, please.